Hi everyone, welcome to today's chemistry adventure. I'm Becky the science teacher, and today we're going to have a look at how the periodic table has been developed over the years as we've discovered more elements. So this is another topic a little bit like the development of the atomic structure, where students often lose marks because again, I feel it's one of those topics because it's hard to think back. It's hard to imagine that we didn't know the information that we know now. And it's almost like a mini section of history within science. And again, if that's not an area that you know works for you, if you're not a history buff, it might be an area where you're less interested. So what I'm going to do in this session again is I'm just going to give you the bare bones, the key things that you need to be able to recall, and so that you can hopefully not lose those marks in the exam, and you'll be able to answer questions of the periodic table with confidence. Okay, let's jump in. So here's our modern periodic table, and in our modern periodic table we can get lots of information from this. We can very easily identify where the metals and the non-metals are. We've got the group numbers, so we've got our columns that are groups. We've got group 1, 2, 3, 4, 5, 6, 7, 0. I know straight away looking at the periodic table that in group 1 the elements in there are all metals, they're reactive, they've got one electron in the outside shell. By looking at what row, so what period they're in, I know how many shells of electrons they have. So if I was to look at sodium, for example, so sodium is over here, what I could tell you straight away is that it's a metal. It's got one electron in its outside shell. It's in period 3, so it's actually got 3 shells of electrons, 2, 8 and 1. And so I can already start to pick out lots of information about these different elements. Now what we've got to try and understand is that this is the modern periodic table. This is based off the fact that we know about protons, neutrons and electrons. We have studied these elements, we know about their reactivity, we know about their properties. But if we're going back, we've got to imagine that when these elements were discovered, from the last session if you remember, we thought that atoms were tiny spheres. We didn't know that there were protons, neutrons and electrons, and so we just had these little balls of different stuff. And so in the early periodic tables, when we didn't know much about the elements and we hadn't discovered many different elements, it was quite easy just to stick them in a list. And you know, if we've only got we've probably got about 20-25 different elements there, it's dead easy if I said to you, you know, can you find me the mass number of zinc? It's quite easy just to look up and down that table and to find zinc and to recall the data from it. We didn't know anything else. We didn't know about protons, didn't know about neutrons, didn't know about electrons. So there wasn't really anything else to do. So in the early models, we simply just listed them in order of their mass. Now as times have changed and we discovered, remember first of all we discovered electrons, so we changed to the plum pudding model. Yeah, and then we discovered protons and neutrons. So as that's changed, we've been able to rearrange the periodic table, plus we discovered more elements, so we needed something a little bit bigger. So the first sort of, I would say, most table-like setup was from a scientist called Newlands, John Newlands, and he used the law of octaves. But again, he simply put them in mass order. He put them in their atomic weight. We didn't know anything else about them. Yes, we might have known that their reactivities, their colours, things like that, but the only real property that we had was their atomic weight. So he simply just put them in order of their atomic weight. And I think one of his ideas is he went for the law of octaves because there's lots of patterns. If you're a musician, I believe, we go off patterns of 8. But he put them into these patterns of 8 and some of them had related properties, some of them were similar in their chemical properties, but we just put them in order of atomic weight. And so when we look here, so some of them you can see that it is similar. We've got lithium, sodium, potassium, and they're all in the same group. That's how we know they are today. But now we know that's because of their electron structure. At this point, it was more by chance that they'd fallen into that structure. Because if we have a look then, here we've got carbon, silicon, tin. Tin's a metal, carbon and silicon are non-metals. That doesn't sort of really fit the pattern, does it? Over here, yeah, we sort of got chlorine and fluorine together. But then we've got cobalt and nickel. So we have some that fit into those groups of chemical properties, but because we hadn't discovered electrons, we hadn't discovered protons, we didn't understand why that was. And so that was fine for the yearling models. But what we're going to have a look at is how Mendeleev changed that. Mendeleev was the scientist that started the modern periodic table, and there was quite a few things that he did that people were unsure about, shall we say. Okay, so let's just make a note of some of the things that Newlands did and then why he sort of wasn't believed, why other scientists didn't trust him. So as I said, he went for the law of octaves. Other scientists were a little bit sort of critical of this because we don't have a clear division of metals and non-metals for starters. So we've got no clear division. Newlands was a relatively young and new scientist, so people often, the more work that people do and the more you get to know and to trust them, the more then you are likely to believe their work. But if he was relatively new and hadn't done much other work, where people go, oh yeah, he did X, Y and Z, it takes time to build up that trust. So looking at this table, and it had no clear division, he was a relatively new scientist, he'd got many elements with dissimilar properties in the same group, so like our lithium, sodium, potassium that are really reactive, and then we've got our copper that's less reactive. We've got the metals and non-metals all jumbled in together, and in some boxes he got two elements in one place. Okay, so there was no clear division, dissimilar elements together, put in the same group, oops, and what do we say, two elements in the same place. Okay, so let's have a look then at Mendeleev. So here is Mendeleev's periodic table, and we can see now by looking at this straight away, we've developed it a little bit. There's lots of similarities to Newlands, but it's a little bit more developed. We've now got distinguished groups. We've got rows. We now call them periods, but we've got them in rows. And we've kind of taken this a little bit more forward. So if we have a look here, you can see we've got hydrogen in a row on its own, which we now know is right because we've got it up there at the top. We've got lithium, sodium, potassium, rubidium. Yes, they're all now group 1. He's put copper in there, he's put it in brackets because he's not quite sure of that, because one of the things that is missing from this table is we don't have that middle section of transition elements. Okay, but we're getting there. we've got a bit more of a division between our metals and our non-metals. Okay, over this side we've got fluorine, chlorine, bromine. Yes, we've got manganese in there, but again, we're starting to see those patterns. We're starting to see what we know now from our modern periodic table. So, what did Mendeleev do? Okay. So Mendeleev, the biggest thing that he did, what other scientists didn't trust, is that he left gaps for undiscovered elements. And that was a very bold move. To leave a gap and say, I know there will be an element that is discovered there, and it will have this type of properties, it will react in this kind of way, it's probably going to have this kind of mass. That was a very bold move. Okay. However, those elements did in time become discovered. So we left gaps for undiscovered elements. Remember, now that we had discovered electrons, we discovered protons, we discovered neutrons, and so we understood a little bit more about their chemistry, how they react, why they react the way that they do. So rather than just put them in their atomic weight, he kind of combined atomic weight and chemical properties. So I'm going to put that up at the top. Because we know from Newland's table that if we simply go off atomic weight, some of the chemical properties don't quite align. So he started to move some of these around. Yes, he's still got boxes at the moment that have more than one element in, but he started to shuffle them around because he realised that actually probably there we've got lithium, sodium, potassium, copper. It's a metal, but it's unreactive. Yeah, so he's placed it there, but he's also got it in a section over on the other side here, in with iron, nickel and cobalt. So he's starting to think about not just their atomic weight, but their chemical properties as well. Okay. So Mendeleev was your sort of leading force, if you like, to the development of the periodic table today. Now, sometimes you are asked questions of similarities and differences between Mendeleev's table and today's table. One of the big things with Mendeleev's table is that there is no group 0, so there's no noble gases at this point. Okay, that is an extension of where the table has been developed, and although he has recognised that, you know, those metals like that copper doesn't quite fit in with group 1, we haven't got that transition element section either yet. Okay, so those are all developments that were yet to come, but he was definitely the pioneer of leading the way to where we are with the modern periodic table. Okay, so let's have a look at some of the questions and just further our knowledge a little bit of what you might get asked around these. Okay. So this is a lower level question, so this is a question that you'll find early on in your exam paper, and it says in here, by 1869 we had about 60 elements discovered. That would be a bit more of a lengthier list, wouldn't it, to be looking up and down, so we needed to do something different. So Mendeleev arranged these elements in a table in order of their atomic weight, but he put similar chemical properties in the same column. So rather than just put them next to one another, so hydrogen, helium, lithium, beryllium, boron, you put hydrogen, hang on a minute, nothing else quite fits that, so let's leave some gaps, let's put the next ones in the next rows. And we've got part of his table that is shown in the diagram. So this is use the periodic table and the data sheet to help you answer these questions. Remember, you are given a copy of the periodic table in your exam. So draw a ring around the correct answer to complete the sentence. The periodic table, the columns, so the columns are known as the groups. Okay, oops, lost my pen. There we are. So they're known as groups. One reason why hydrogen should not have been put in column 1. We know it's got 1 electron in its outside shell, so in a way it kind of does belong to group 1. However, hydrogen is a non-metal, whereas the other group 1 elements are metals. So it isn't a metal. Okay, in 1895, the first new family of elements were discovered. One of those new elements was called helium. Where has a new family of elements been placed on the periodic table? So that is now our group 0, or our group 8. If you said it's to the left of, to the right, sorry, the left and right's the wrong way. It's to the right of group 7, that's fine. But we call it group 0, or the noble gases. And the final question, in the periodic table on your data sheet, the elements are arranged in order of their atomic number. So this now, the modern periodic table, is arranged in order of their atomic number. Remember, that's their proton number. When we didn't know about the existence of protons, we couldn't put them in that order. Yeah, so the proton number, remember, defines what element it is that we're looking at. Okay, a little bit then about Newlands and then comparing it to Mendeleev. So in 1866, John Newlands produced an early version of the periodic table. Part of the table is shown below. Okay, so it says iron does not fit the pattern of column 7. Why? Let's have a look at what we've got in column 7. We've got oxygen, we've got sulfur, and then we've got iron. Oxygen and sulfur are non-metals, iron is a metal. So the reason why it doesn't fit is that it is a metal. Okay, in 1869, Dmitri Mendeleev produced his version of the periodic table. Why did he leave gaps for undiscovered elements? And that's so that elements with similar properties could be placed together. So remember, he went off mass and their properties. Okay, so Newlands and Mendeleev placed elements in order of their atomic weight. The modern periodic table places elements in order of their atomic number or their proton number. Okay, and the final one, lithium, sodium, potassium are all in group 1 of the modern periodic table. Explain why. And this is because they all have 1 electron in their outside shell. Again, and when we didn't know about the existence of electrons, we couldn't put them in that order. We didn't know why they had that chemical property. But now we know that the number of electrons, and particularly in the outer shell, that's what gives them their reactivity. So similar properties, and so they're in the same group. Okay, and on to our final one, which is a bit of a higher level question. So read the information about the periodic table. So here we've got in 90, I keep saying 19, don't I? 18, see what I mean? It's hard to try and think back, isn't it? In 1869, Mendeleev classified elements by first putting them in order of atomic weight. He arranged them in a table so the elements with similar properties and reaction were in columns known as groups. He also left gaps for undiscovered elements. Okay, so use your modern periodic table on your data sheet to answer the questions. Some elements were not placed in order of atomic weight. So in terms of properties, suggest why potassium, which is atomic weight 39, should be placed after argon, which is atomic weight 40. So in our periodic table we should have potassium and then we should have argon. However, if we put them that way, we've got potassium in a group of gases, so really reactive metal in a group of non-reactive gases, and then we've got argon, which is a non-reactive gas in a group of highly reactive metals. So what he did is he would just switch those around. So rather than simply relying on just mass, he went mass and chemical properties. Okay, so we could say that potassium is an alkali metal, or it's group 1, or it's reactive, something along those lines. You can also answer this question the opposite way around by saying that argon is a non-reactive gas and therefore needs to be in that column. Some scientists thought that Mendeleev's table was not correct. Suggest why by referring to the elements in group 4. In group 4 we do have, that's where we see that slight division. When you put your aluminium steps on your periodic table, that's where we have a mixture of metals and non-metals, and therefore, you know, there was that idea about, well, is it right? Because now he's jumbled up his metals and his non-metals. Okay, and the final question. In 1890, the new group of elements, group 0, was discovered. Suggest why they were easily fitted into Mendeleev's table, and that is just because they fit on the end of what he had. Didn't need to make any adjustments, they just very nicely fit on the end of the table. Okay, and that is how we've come to what we know as the modern periodic table. So that's it for this session, guys. We've broken down how the periodic table has been developed, and hopefully now giving you a bit of an understanding of why we changed that upon the development of the atom. So we needed to change our ideas and change that idea of the periodic table. Okay then guys, please feel free to reach out if you need any further support. Otherwise, I'll see you next time.